Hello, everyone. Many thanks for participating in the IROS 2023. This work introduces an evolutionary-based online motion planning framework for quadruped jumping. Jumping motion in challenging natural environments is the critical component of quadrupedal robot. Some popular methods have been released to show the impressive results, such as left one using RL to jump and the right one use first-order gradient-based method. They usually need learning from data offline or online, and sim to real, or need to construct convex QP problem with complex dynamic constraints and usually need to a predefined trajectory or time allocation. Question: can we find a unified framework to produce various jumping motions online without added information and just solving a black box problem? Here, we proposed an online evolutionary-based jumping motion planning framework, which does not rely on prior knowledge. In our framework, we intend to answer the following questions. 1. How to design a time-friendly optimization framework for online motion planning using an evolution-based technique. 2. How do the configuration space, latent hypercube sampling, and optimization variables transformation accelerate the convergence speed of the optimization? 3. How to produce a series of trajectories for the pre-motion library. You can see the green box in the framework diagram. Before construct our problem, we need to show the model and dynamics. Based on a general assumption of single rigid body and there is no compound rotation of body, and planar model with two legs is captured to describe the jumping motion. Meanwhile, for our framework, we categorized the jump motion into 4 phases according to the contact between the feet and the ground. The right part is the robot state, Euler and Netwin equations. This is our optimization problem and objectives. Unlike the gradient-based method, our evolutionary-based optimization framework's cost function is a well-designed priority hierarchical fitness function. What is prioritization fitness function? Considering the hardware and environment limitations of the robot, we introduced the following constraints in our jumping optimization framework. The convergence speed of the optimization algorithm can be accelerated by giving different priorities to different constraints. Then, how do we solve the above optimization problem? Jumping motions of the quadruped robot can be realized by planning the contact force of each feet. The contact force of different jumping phase can be expressed in a polynomial equation with respect to time. However, the range of the contact force coefficients are not clear, which makes the optimization problem difficult to solve. So by substituting contact force into simplified centroidal dynamics and integrating, we can obtain jumping motion states of each jumping phase with respect to contact force coefficients, jumping phases duration and initial states. Thus, contact force coefficients can be converted into parameters with physical meaning. And this is the robot kinodynamics constraints. To accelerate the optimization search, we create the COM configuration space to compress sampling and search space. The right figures show the configuration space of different plane. Here, show how good latent hypercube sampling was introduced in our algorithm. You can see the significantly decrease of the iterations. And the right one show with a pre-motion trajectory, we can decrease our sampling space again so that we can satisfy the online optimization requirements. This is our online DLC algorithm. We use the part of conventional differential evolution algorithm method, and CAR fully designed priority fitness function with kinodynamic constraints and energy consumption. Here, we restrict our sampling space and configuration space in line 2. And we replace the random sampling to latent hypercube sampling in line 5 and 7. And the right figure show the time consuming with pre-motion with proposed online DLC algorithm. The proposed framework has been successfully validated only with a simple continuously tracking PD controller in an updated and no software limit open source mini cheetah by several challenging jumping motions. Here, show the flipping motions and continuous jumping. The algorithm can handle all of them. To the conclusion, a time-friendly online motion planning framework for quadruped jumping based on the meta-heuristic differential evolution, latent hypercube sampling, and configuration space, DLC, algorithm is proposed, which can generate various jumping trajectories online.